Hello everyone, Namaste. I am Ramnath who would like to present you the key learnings from chip development part 8 on synthesis of RTL design. This is a continuation of part 7 which was covered already. In this presentation, I will briefly mention the key steps involved in the synthesis. For more details, please refer to the references. And thanks for learning along with me. Feel free to provide your suggestions. Thank you. To understand the synthesis portion, we will observe that RTL design is the first primary input, which is very essential, where the design intent is represented in an abstract manner at a high level. And this design where it can be implemented either in a synchronous operation or in an asynchronous operation. Largely, the synchronous operation, the design will, when implemented, will contain a set of registers, especially implemented either a D flip-flop or any other type of flip-flops. It can be RS flip-flops, T flip-flop, different types, but usually the D flip-flop is preferred. And this can be further improvised into scan flip-flop for test insertion. That is the next level. So during this synthesis conversion, the design is mapped to uh, logic gates. For this purpose, you need technology data. This technology data can be for digital logic implementation purpose, where we are mainly discussing, you need standard cells and memories and IOs and analog blocks. Especially the memories, analog blocks, and IOs, they will be instantiated at specified locations. And coming to the standard cells, since they are millions, they will be grouped as per the technology specific design constraints. In the design constraints, the chip level information is provided. So here they will be providing what are the IO pins, where they are located, how IO pin are positioned with respect to the design. That means like indirectly what is the drivability of the IO and how the input pin is driving the digital logic and how it will drive the output logic. And you will also mention there are any multi-cycle paths or false paths and what is the clock period and are there any virtual clock. All that information will be mentioned in the design constraints. Aside to that, it will also give some more information about the standard cells multivariants. All these, how, if at all, if there are any, don't use cells need to be mentioned, and don't touch macro blocks need to be mentioned. All that information will also be contained in the design constraints. So when this step of synthesis is processed, this is a pure logic based synthesis. Okay, so in this logic based synthesis, mainly the RTL design will be converted into small into the respective logic gates. Okay, so at this stage, and these technology specific gates from so and so technology, say either 28 nanometer technology or 5 nanometer technology or 2 nanometer, all that will be instantiated. Corresponding logic gate will be instantiated because this is the input supplied. So the design is converted based on this technology gates, say whether inverter or NAND gate or flip-flop. This gate, once it is realized, it will be converted into that gate. So this is called logic synthesis. So This is one step closer to implementation of abstract level data into gate level data. Aside to that, we can also perform the physical synthesis using the same inputs. So for that, we need to include the floor plan data of this design. For that, we have got certain design data during the logic synthesis. During logic synthesis, whatever design we got, based on that, we need to arrange the macros. These macros can be either memories or analog blocks or anything. So those data, if you are providing their placement locations and the specific instance locations of the this design as a floor plan data to this physical synthesis tool. Physical means you are providing the placement and orientation, all that information of the macros. That is why it is called a physical synthesis. Now it will take these macro data and the RTL and it will go for the one more route. So during this time, you will get a better uh, digital implementation, which is shown in the pink color. So now this data this is now it will be a more better representative of the RTL design with respect to the design constraints and the technology data provided. during this synthesis part, especially the RTL compilation and elaboration step, especially during the compilation step, the it basically parses the HDL code and ensures that it is syntax wise it is correct and the ports are properly specified and whether the connections are properly hooked. So all these checks will be ensured and it will ensure that the design, the compiled code is ready for elaboration. The elaboration step will take the compiled pseudocode which is in and process it further. So during this process, it resolves the HDL module instances, parameters, and it will generate a complete design hierarchy. This design hierarchy actually will represent the entire design. That means the HDL code of the RTL. So now if you observe carefully, this design will contain all components and their how they are linked and how they are related. All that information will be existing in this portion and this will be ready for either simulation or further synthesis. This is the key step. Okay, so this step is further modified later as per the design rule checking and logic optimization phase. So in this step, the modules are connected, hooked and connected. So signals will be moving from one module to the another as per the RTL design and the blocks and their hierarchy, everything will be specified. Thus, this will be a ready-to-go design as far as the RTL elaboration is concerned.